Can I get rid of that? Yeah. Sometime tonight, because I can at least post PowerPoint tonight, because you might want something to reference. It's important to note that when we're going through this, a lot of resources, so if you have the Meisler textbook from Inorganic, they're going to use very similar equations and approach this very similarly, but they don't go over Raman. They just talk about the normal active modes. If you use like Chem Libre text, Catherine Haas has a whole thing going through this, but I'm pretty sure there's a typo in it. So she gets a different number at the end, even though she gets the same result. But there are a lot of resources for this. I'll probably post the Meisler, like what pages in Meisler textbook it is, because that's a really good textbook and it goes over it well. If you have Symmetry and Spectroscopy by Dover Glenn, also very good, but a little bit more complicated terminology.
Also has all the tables in the index.
Yes.
Yeah.
You can get your character tables from anywhere. I use the Jacobs website from some university. It's what I've used since undergrad, so that's where my tables are taken from, but they're all the exact same. So wherever you want to grab them from, go ahead and grab them from. But yeah, any questions before we hop into talking about symmetry? Cool. Maybe. Cool. Oh, can I get rid of this? Hide? Hide floating meeting. Oh, okay, we're good. So if we want to figure out vibrational modes of something, there's ways that we can predict them. And typically we think about it. Why? You good, Red?
Yep.
Okay. Typically we think about the equation where we do 3 times the number of atoms minus 5, something that's linear. So something like carbon dioxide, we can do this. And if we do 3 times 3, we get 9, minus 5, we get 4, right? That's math, yeah. We get 4, so we have 4 vibrational modes. If we have something nonlinear, like water, we do 3n minus 6. And here we would get 3 vibrational modes. But this doesn't really tell us how many IR active bands there are or Raman active bands. So if we want a little bit deeper exploration into the possible vibrational modes, we can use symmetry. So if you remember from symmetry, we have our symmetry operations and point groups, and that's going to be the base of what we're doing. So with symmetry, if we're using water, for example, the axes are drawn on the right. This is how we'll always orient them. If you need to change where your z-axis is pointed, rotate your axes. So starting off, z will be up, y will be coming out of the page, x is to the side. And if your z is like coming out of the page, you want to rotate all 3 axes. So if we need to evaluate symmetry operations, what's the first one that we can do on water?
Flip it over.
Oh, what does everything have?
Oh, identity?
Yeah, so we can do an identity. Now, you're right, we can do C2. Where would I do that rotation?
Through the
Oxygen.
Yeah, we're going up and down through the oxygen, so luckily I already aligned the axes to be the right way. So our principal rotation axis, Z, is going to be aligned with our principal rotation axis. So you're going to rotate on that oxygen. What's another one that we can do? Does it have any more rotation axes? Axes.
Oh yeah. Oh, my brain immediately goes to the internal one, but I forget its title.
Internal one.
I'm gonna pull up the one second.
Through itself?
Yeah.
Well, can it invert? Nah, I can't invert. Because then we'll have our
Your hydrogen ends up in thin air.
Yeah.
What about reflection planes? Are there any reflection planes?
Oh yeah.
What's one of them?
Also straight through the oxygen.
Yeah, so we either can go, if we have vertical reflection planes, we will not call it vertical. We're going to call it based off the axes that it's aligning with. So the first one that we can do is on our XZ axis. So can I grab my pen? We'll try. Sorry if you get a weird angle of Brett there. So if we look at our X and Z, we're basically cutting a plane this way. That was a horrible square, but that's a square. And we're cutting it right in half. And that would be our XZ reflection plane. We have one more. We can do it on the YZ. So now we're looking at, can I draw this right? I'm really bad at drawing these, but now we're cutting right on the YZ plane, right between the oxygen. So now that we know all the symmetry operations, we also need to assign its point group because we're going to need the character table. So this is the one that was used in 310 one semester. I don't know, was the same one used last semester? And Red, you took 310 with Ray.
Yeah, Dr. Shock. And his was different, but I mean, it gets the job done.
All right, so let's go through this table. So for number one, is this low or high symmetry?
This is
Or neither, sorry. 3 options here.
Excuse me. This is lower symmetry.
But is it low? Is it a C1, a CS, or a CI?
No, so it
No.
isn't.
So now we're gonna go to number 2. What's the highest rotation axis that we found?
C2.
2.
Awesome. Now, are there perpendicular C2 axes?
No.
No, yeah, because we only have one on our Z. I can't go on my Y and rotate at 100, and I can't go on my X and rotate at 180. Is there a perpendicular plane of reflection? If
Yes.
Z is up and down,
Oh.
is there one that's on our YX?
No.
No. And we know we have 2 reflection axes. I hate it. Axes. Axes.
Stick with the natural X. The S on it.
My head wants to say axis. I can't say it now. But yeah, we have our vertical reflection planes on our ZX and our YZ. Can you go away? Nope. Okay. So what would the point group of this be then? The end.
C2V.
Awesome. So yeah, before you go through any of the problems, you'll have to go through the first 2, which have you identifying the symmetry operations and the point groups on your pre-lab. So you'll just follow these exact same steps and just try to draw the operations as best as you can. It's sometimes hard to indicate reflection planes or rotation where it's rotating. So once we get, oh yeah, Red?
Should we use something like PowerPoint that can generate like squares and circles like this to try and draw it, or is
Do
it okay?
whatever you're comfortable with.
Okay.
Yeah, I'm fine with however you want to do it. As long as I can kind of understand what you're indicating, we're good. Alrighty. Now that we have our point group, we want to identify the character table. So again, these are in textbooks. You can find them online, however you want to do it. But here's our C2V character table. We're going to use this for a lot of things for this set of problems. So now we need to calculate the reducible representation. I assume both of you haven't done anything with reducible representations, right?
Nope. The last thing we did was as far as we went.
All good. So essentially what this means is we're just calculating all the modes that are possible for it. It basically puts its matrices into a more understandable way. So we won't be doing matrix math because I don't know if either one of you have taken linear algebra or matrix math yet.
I've taken like 2 different courses that are like, oh, if only here's the linear algebra portion, but they never require us to take linear algebra. It's just in there.
Yeah, so there's a shortcut method to it, so we don't need to do matrix math. So we'll do the shortcut version. So the first thing we want to do is identify the contributions from each axis. Did I get that there? Awesome. During each symmetry operation. So however we aligned our axes, we're going to put them in here, and then we're going to figure out what's happening to them as we go through each operation. If something moves, we're gonna go a -1 contribution. If it stays pointing in the same direction, it's a +1. So the way we're gonna do this, X, Y, and Z, this will be 1, 2, and 3 on the contribution line. So for E, are any of my X, Y, or Z's moving?
No.
Stays the exact same. So each one contributes +1, and we get a contribution of 3.
Oh.
For C2, remember our principal rotation axis aligns with C. Are any of the axes moving?
X and Y.
Yeah, our X and Y rotate 180 degrees. So now our X and Y are both contributing -1, and our Z axis is contributing +1. So I probably should have added that down here. Z, X. Red, you can see what I'm drawing on the screen, right?
Yes.
Cool. So now we have a -1 for our C2. What about, I was like, I didn't put the little thing here. It's because it's in all the boxes. It's been a long day. That's fair. On all of them, I have like the drawn, and I was like, why didn't I put it here? It's already on it. All right. Now for our reflection on X and Z, is anything moving?
No.
No?
Oh yeah. X, X
Yeah.
and Z.
Our X and Z stay the same, and our Y gets flipped. So this kind of tells us
Oh, I'm thinking of the
what's staying the
spectrum.
same. So our Y is now pointing in the opposite direction, meaning our X and Z contribute +1, our Y contributes -1. And for this reflection plane, we get a +1 contribution. Now, how about for our Y and Z? Is anything changing?
The X.
Yeah, great job. Now we're just flipping over the X-axis. And similarly, our Y and Z are staying 1, and our X is -1. And we get another +1 contribution. Does this make sense for how we got the numbers, how to go about figuring out which one's staying the same and which ones are in different directions? Yeah. Okay. Now, I think one of the complexes you'll work with is C2B. I'm not entirely sure, can't remember, but one of them isn't. So you're gonna have different symmetry operations. So you'll have to go through this again. This won't change. So if you have EC2 reflection of XZ and YZ, you'll always get these same contributions. That doesn't mean your reducible representation is going to be the same, but this part of finding it will be the same. Red, do you have any questions?
Nope. This makes sense.
All right. So the next part to find our reducible representation is we have to consider atoms. No, we can leave.
He was up to 208 at.
Yeah. It's 1:30.
1:30, yeah, I don't mind.
Oh,
Okay,
good.
no worries. Thanks.
All right. Red, we're gonna relocate for a second.
Sounds good.
Maybe if I can get untangled.
Want me to carry anything?
Red, bear with me as I'm carrying my surface. No, don't worry. Is that fine with you? Yeah, I mean, that's fine. The new award. Haven't seen it yet.
Yeah.
Oh.
Yes, it is.
Wait. I don't know where you want to sit, Brett, to make it easy for you to see. Oh. Okay. Brett, can you still hear us?
Yes, I can.
Cool.
Yay.
Awesome. Sorry about that. We were occupying a space that was previously scheduled. All right.
Oh.
Good.
Hmm?
Awesome. So continuing with our reducible representation, we also need to take into account our atoms. So here it's a kind of similar trend where we're going to go through each symmetry operation with the compound that we have. If a atom moves, it's now 0. If an atom stays in the exact same place, it is +1. So here I have the hydrogens different colors, but they're both still hydrogens. It's not a carbon because it's gray, it's a hydrogen. I just wanted to be able to illustrate the movement. And then going from left to right, our first hydrogen is going to be 1, our oxygen is going to be 2, and then our third hydrogen is going to be second hydrogen is going to be 3. And it's going to match up with the contributions on the bottom when we're adding things. So if I go through E, is anything moving, anything changing?
Nope.
No. So I have 3 atoms, they all stayed in the same position. So they all contribute +1. If I had 4 atoms in the same position, it'd be +4. If I had 10, it'd be 10. Now what about with C2? Is anything staying in the same place?
Just Brett.
Which one?
The oxygen stays.
The oxygen is. Both our hydrogens get switched because we just did a 180 rotation, but our oxygen stays. So what's the contribution here?
2.
Things move at 0, things stay the same, it's 1.
Yeah, 1.
Yeah, 1. So 0 for both our hydrogens, 1 for our oxygen. Right, what about if we reflect on our XZ plane? How many things are staying the same?
It's all the same, right? So 3.
Yeah, because we're just reflecting right through it. So technically the atoms haven't moved. So it's +3. Now what about our YZ plane?
Same as the C2.
Yeah, same as the C2 because both our hydrogens have switched positions now. So while symmetrically it's the same, since our physical atoms have moved, this is why it's the contribution of +1.
Yeah.
Does this part make sense?
Yeah.
How about for you, Red? Makes sense?
Yeah.
Any questions? Oh, let me put in the last thing.
Yeah, it makes sense.
All right. Now, things won't always be 3. Remember, it's based off the number of atoms that you have. So if you have 5 atoms, E is 5. Whatever C2 is for a thing staying the same. All right. So now that we have our contributions from both the atoms and the what is happening? The axes, we're gonna multiply them together. So we line them up again based off their symmetry operation. And then we multiply them. So for E, what would be the reducible representation? 9, yeah. C2,
-1.
great. Reflection plane on our XZ.
3.
And YZ.
1.
1. So when we write a reducible representation, typically people just write, I think anything else pops in here. You do gamma, red, and then 9, -1, 3, 1. So that's like the standard notation. Some people write it differently. You can put it in a chart if it makes it easier for you. I'm not going to be a stickler on notation because I'm not a symmetry professor. I'll use some different notation than you'll see in some of the textbooks because it's the way I learned. As long as I understand that you get the right numbers at the end and they're organized based off how you organized your symmetry operations, I would say just follow the character table when you're organizing things. Don't put them in a weird order. It makes your math easier much later. So yeah, that's the first thing. Calculated our reducible representation. Now we need to calculate the irreducible representation. So math. So this is a very scary looking formula. I promise it's not that bad. So A is the number of irreducible representations for a given type. We'll get to that in a second and what that means. H is the order of the group. Do you both know what order means here? You can say no, that's completely okay if you don't. Red, do you know what order means?
I'm gonna say no.
All good. So if we look at our character table up here where our symmetry operations are, we're going to take the number in front of each one of them and add them together. So technically, these are all 1. But on different character tables, sometimes you have multiple C2 rotation axes. So you'll see 2 or 3. Here, just 1. So we take all of those. There's 4 operations, and all of them technically have a 1 in front of them. And that gives us an H of 4. So there's 4 total operations.
Yeah.
So that's what order means. We're just adding the numerators on our symmetry operation. So again, if there's a number in front of your C2, in front of your sigma V, or in front of your sigma H, you also add that number. It's not always 1 + 1 + 1 + 1. Pay attention to what the character table tells you. Then we also have n is the number of operations in the given class. Again, this would just be the numerator. When we get into the math, it'll make more sense why n and h are the same color. R is going to be the reducible representations. Oh, I did it. Why did I color it that way? I should have switched those. N is our reducible representations. And then I, R are the numbers in the middle. Still confusing on how we go about this math. I know this is just what the things mean in here. This equation exists in many different forms. Whatever form makes sense to you. This is the form I learned when I took inorganic. Meisler has a slightly different equation. Actually, I think it's the same equation. They just don't use variables. They just have a bunch of words written down. So it basically says the exact same thing here, just in big parentheses. So we'll go through the math now because I know looking at this equation isn't very helpful. So we have to go through each column, row,
Rows
cross.
across. House.
You're right. Okay. I have to look it up. I think half my search history is column versus row.
Okay.
It's one of those things I'll never remember. So we have to
Slow
go.
down your hand.
We'll go through each row and use the numbers in it. So when we set this up, we do 1 divided by our order, so 4, and we're going to multiply that by the summation of everything. So we start off with the symmetry operation number, which is 1 for E, multiplied by our irreducible representation for E, our reducible representation for E, multiplied by that first number in the chart for E at A1, so that +1. So we have 1/4 order, 1 from our E, 9 from our reducible representation, and 1 from the matched up box for A1 and E. And we're going to do that for every single operation. So if we go,
That's the character.
yeah.
Characters in the box.
It's been a long day. I'm doing my best. So going on to C2, again, we only have one C2 operation, so that's why there's a 1 in front. If we look into our reducible representation, it's -1 for C2. And if we look at the character in the table, it is +1 for C2 and A1. We move on to our sigma XZ. Again, they're all going to be 1 for this one. I only showed it here because, again, sometimes things aren't 1, but 1 for the number of operations, 3 for the reducible representation, 1 for the character in the table. And for the last one, 1 for the number of operations, 1 for our reducible representation that matches up with our YZ, and then 1 for the character in the table of A1 and YZ. We do all that math, we get 12 on the inner parentheses, and we divide that by 4, our order, we get 3. Now we gotta go through this for each row on the table. So I just shifted it up. This is technically right below A1, just to save room on it. But now we're in A2. We're gonna set it up the same way, where the only things that we'll see changing are these green numbers now. Sorry, I'm at a weird angle, Red, so please apologize, or I apologize for my wonky writing. So now we're just matching these up with our A2 characters. We do the math. We get 1. Do you guys want to try? It's gonna pop up. Never mind. I was gonna say try the next one, but I should have put the table up.
You can try it. No, they don't have the characters.
I was like, if I go back.
Back to the table.
All right, we're gonna go back real quick.
Sure.
All right. Take a picture of B1 real quick.
Okay.
Red, you good on B1?
Yes.
Awesome. Now go ahead and do the same math with B1. Let me know what y'all get.
Huh.
Ever not divisible by H with a integer?
If you ever get something that's negative, a fraction, you've done something wrong. I think the Meisler book says the same thing. It's like, get a fraction, something is
Go back,
wrong.
go back there.
That's -1 plus.
I have a value, that's good.
You have a value.
Not a fraction?
Not a fraction.
Oh.
Scared for a second.
But
Did do them.
it's like kind of helpful, you know, like if you get a fraction that's like an actual fraction, because you're always going to end up with
Yeah.
a fraction, but like an actual fraction, you know that somewhere it went wrong.
Okay.
All right, what did you get, Red?
7/2.
Something went wrong.
Yeah. 1 second.
No, you're good. Don't worry.
1. Okay. It's just, oh, my eyes skipped. I see what I did.
I don't think anything that we'll be doing in this class will require a lot. I think the most I've ever had to do is like a D2H or a D2D, and that's like a lot
A
of
lot of
these.
operations.
Yeah, a lot of them. It was on an exam. It was not a fun time. To be fair, it was COVID, so they made all our exams much harder since they were take home. And we had 48 hours to do it. But it was not fun. It was like 2 pages of paper just for one question. Fred, did you get a new number?
Yeah, so 1/4 times 12, which is 3.
All right, so Brett got 2, you got 3. Let's take
Oh
a look
gosh.
at it.
Oh, okay. Wait, yeah. Yeah. Okay.
Let's see.
Oh, I have that as -1. That's supposed to be 1.
So my initial mistake, aside from my eyes jumping to my A2 line, was I I was overcomplicating it. Because the purple number is just 1, you can just take whatever's in the line and then
Yep.
multiply it by what are we calling this again?
The
The
character?
or the red
Oh, the
uh
reducible representation.
reducible. Okay, cool.
I caught B1 down wrong.
So yeah, just be careful because it's really easy to miss like a negative or a positive here, but there's a good way to check at the end of all this. So we'll go ahead and look at B2 then. B2, we get 8 divided by 4. Again, all we're changing at this point is just the characters, so just the green values. Once you set up the first one, the rest are just changing the green values, which will only change the sign of something, or I say the sign. It will change the number eventually, but in this case, it's just going to change the sign. We're not going to deal with any character tables that have cosines in them, so you don't need to worry about the complicated math of dealing with that. But it comes out to pretty numbers at the very end, even if you have trig terms in it.
You just suffer along the way.
Yeah.
So this is how we calculate the irreducible representation. To represent the irreducible representation, we take the number, and what it matches to on our table. So for the first one, we got 3, and that was for a row, or a 1 row. So we have 3A1. And then we go down and do the rest. So 1, A2, 3, B1, and 2, B2. Now at this point, we can also make sure that we didn't make any mistakes. We love a little checkpoint while we're doing math. So here, however many irreducible representations, or the sum of our irreducible representations, should equal 3 times n being our number of atoms. So if we're looking at water, we have 3 atoms. So if I do 3 times 3, I get 9. And adding up the numbers in front of all these, I should get 9. And I do. So we're doing good. So like Brett, if you thought it was 2 for the previous one, here you would have been like, oh, I got 8, something went wrong. So try to take like a break when you're doing your pre-lab to look at this and check if you have 3n once you get your irreducible representations. A few more steps. We good, Red? Do you have any questions?
No, this makes sense.
Math makes sense? Scary formula. Math is pretty, not straightforward, but
Oh, wait. Is this entire formula is just doing this table thing?
this formula right here is one of these.
Oh, wow, yeah, that's
A1 is the like irreducible reps of a given type. So the type is A1, A2, B1, B2.
okay, cool. That's a
yeah,
lot of big symbols for something that's pretty straightforward.
yeah, it's just saying like we're summing up each one of these. So like one of these is this, and we're summing it up for all the characters in that table or in that row.
Mm-hmm.
And that's why there's a lot of different ways you'll see this equation. I like this way, but I've also taken matrix and linear algebra, and like I'm used to seeing it this way. The Meisler book is a much more friendly way. It's just the words in the equation. It's not all the fancy symbols. All right, any questions?
I like this.
Math is mathing. This is
Yeah.
good.
And you can check yourself, which is also really great. All right. So now we need to calculate the vibrational modes. Like we've done all this, but we still don't know what's IR and Raman active, and we don't know which ones are going to be. So to calculate the vibrational modes, we have to do a little bit more math. This is just subtracting things. The way we're gonna do this is we need to first locate our linear functions of rotations, which is this column right here. And we're gonna subtract our translations. So translations in this are going to be our X, Y, and Z. So if I look at my linear functions and rotations column, my X, Y, and Z are highlighted, and I'm going to subtract each one of these. Say I had Z and X up here, it would be 2A, not 2A1, not just A1. But we're just going to subtract each one. So we get 1A1 because it's a Z contribution, 1B1 because it's a B or X contribution, and 1B2 because it's a Y contribution. Again, say this was like X, it would be minus 2A1. Can you guess what the rotations are going to be?
2, 1, 2, and 1. Or am I not taking this?
I understand what you were saying, so yes. My question was more broad than that, like, what are they going to be labeled as? They have R's in front of them. There are RX, RY, and RZ. I know, we're so creative. Rotations are labeled with R. So similarly, we're gonna find those in our table and subtract them. So our rotation modes are our A2, B1, and B2. Any questions so far? You doing good, Red?
Mm-hmm.
Awesome, awesome. So once we figure that out, we're gonna subtract them. So we get rid of one of our A1s, which leaves us with 2A1. Our A2s are taken out. We're subtracting 2 B1s, so we're left with 1 B1 and 2 B2s, so our B2s are taken out. Now we're left with our vibrational modes, or our vibrational representation, which is 2A1 plus 1B1. And here's another point that we can do a check. So if you remember from the first slide, we know how many vibrational modes should be possible for a nonlinear molecule if we do 3n minus 6. So we have 3 atoms. 9 minus 6 is 3. So we should have 3 vibrational modes. And if I do 2 plus 1, I have 3 vibrational modes. Now we've gotten to the same point that that really easy equation on the first slide gave us. But again, we still don't know how many IR or Raman active modes they are. So we did all this work just to kind of tell people the same thing that that nice little handy dandy equation could tell us. We want to be more specific about things. We're going to figure out our IR and Raman active modes now. So to figure this out, we're similarly going to use the table. I blocked out A2 and B2 because it's not part of our vibrational modes. So we're not going to look at them at all. So IR vibrations are going to be X, Y, and Z. So if something's labeled X, Y, or Z in our linear functions column, that's going to contribute to our IR active modes. So here, we only have X and Z because Y is part of B2. We don't have any B2 in our vibrations. So this tells us that in IR, we can have 3 possible active vibrations. That doesn't necessarily mean we will observe 3, just means that there are three possible ones. They could be overlapping, one could be silent. We're not going to talk about silent modes here because beyond the scope of my knowledge in this class. But there are three possible IR modes because we have Z and X, A1 and B1, and A1 and B1.
That is actually really cool.
I think like if you theoretically plot the IR for water, you do get three modes, but if you actually get the IR, you only get two peaks. Because there's the anti-symmetric and symmetric stretching. And then there's one other one that I'm forgetting about. Maybe it's the lagging. No, it can't be the lagging. But you usually only see two, but like idealized, you get three peaks. Now for the Raman, we're going to look at the binary products. So that's anything that's XY, YZ, anything that has two things in it. So here, we're focusing on the quadratic functions column. So this column here, we won't deal with the cubic functions column. Don't worry about that. I don't even know what that does. I've never dealt with it. Again, beyond the scope of this class and what I know. So if we look at this column, both A1 and B1 have binary products in it. So similarly, our Raman active nodes or modes are A1 and B1. And again, we have three possible active vibrations because our vibrational modes are completely made up of A1 and B1. And that's how you figure out your IR and Raman active modes using Symmetry. Are there any questions?
So it doesn't matter how many binary products or linear functions there
Yeah.
are.
The only time that we care how many is when we're calculating out, where is it? Go back here, because then we're subtracting based off that.
Yeah.
But once we're here, it's just telling us like this is an IR active mode and this is a IR active mode. That's all. And it's going to be based off our vibrational representation. So I'm certain like there are some, you can do more studies on it and actually look at like the bonds and how they're folding to figure out which ones are truly IR and Raman active, but again, beyond the scope of this class, and that requires more representations.
Yeah.
So here we're just looking at which ones are technically possible. Even if they may, I don't think anyone here is technically IR silent or like a silent bend or stretch. AU is typically silent, but again, we're going to disregard that. You're just going to go through these steps. And if you go through these steps, whatever matches up at the end.
Okay.
Red, do you have any questions?
I do not. I might after giving it a go though.
Yeah, so your entire pre-lab is going through each one of these steps. It's 6 questions, all going through the exact same steps as this. It doesn't have like telling you to do the checkpoints, but use the checkpoints when you get to your irreducible representation and your vibrational representation. You have 9 atoms instead of 3 and slightly different point groups. So you're going to get slightly different results than this one. But again, you have checkpoints so you can kind of make sure that things are going okay as you go through it. And I'll be around all day tomorrow. You know, you're always welcome to email me or just stop in the office. Yeah, are there any questions? Does this make sense?
Yeah.
Can you replicate this on a more complicated system?
I think so. Just take some time.
Yeah, I think the only bit that I missed was probably because I was taking notes, but what was the check for the second time you could check it?
So right here, once you get your vibrational representation, we can check with that 3n minus 6 if it's a nonlinear molecule, where it's for atoms. So we have 3 atoms for water. So 9 minus 6 is 3, and that tells us how many vibrational modes we should have.
Ah,
My
okay.
vibrational, I do 2 plus 1, and that gives me 3. So yeah, everything up to the 5th step basically gets us to the same place that first slide technically got us to, but we need to do all 5 to figure out the 6th step, which is identifying the IR and Raman active modes.
Sounds good.
All right, if there's not any questions, I think that's all that I have for today.
So are we gonna do another MO lecture? Or how does that?
The goal was, since the 4-hour lab period, I don't think it's gonna take them 4 hours to do
So
the
do it the
DFT.
same.
Yeah, so like we'll start off the lab like going through like a practice example like water or ammonia with DFT, and then they'll have a worksheet to follow for either tungsten. I think I chose tungsten carbonyl and then one other carbonyl because it's pretty like stable. It's a well-documented DFT complex, maybe chromium or cobalt. I don't know. There's a lot of papers on it. That's why I chose it, because then they can read through literature and try to understand DFT literature and struggle a little bit. It's gonna hurt, but that's part of the fun.
He thinks your pain is fun. You hear
Yes.
it, heard it here.
There'll be guided questions. You'll know what you're looking for. But yeah, we'll sit in the computer lab and then we'll do all that in one sitting. I don't think it's even going to take the full 4 hours, maybe like 2 to 3, depending on how long it takes them to like learn to use Gauss view, because that's the hardest part, is building the molecules.
Do we have a computer lab yet?
I don't know.
Forgot.
I was like, we could do it on the laptop, on their like devices. It's all up to them because they'll be logged onto the supercomputer, so it's not like it's using their memory or anything like that. It's you're remoted in. But
Okay.
just depends. Like, I think a computer lab would be nice, just so we don't need to like require students to bring in a laptop.
I think Davy Library is probably the most likely spot to.
Yeah, it's fine.
We can
And that reminds me, you guys have to sign up for ROAR access for this week. Once you sign up on Friday, I'll put up another assignment that's 0 points.
I got a message that Red had signed up, I think.
Ooh.
Right, Red?
I signed up. I don't know if I got an email back if they confirmed that I have access yet or not, though.
Yeah, they sent me as the PI for confirmation, so.
Mhm.
Yeah, that's enough.
Yeah, so there's instructions for how to do that on the assignment page. Once you get access, let me know. And I'll tell you the next thing to do, because we have to make sure you have access to Gaussian. Usually they're pretty quick about things, but we want to give them time just in case they're not.
Yeah.
All right, are there any questions?
I don't think so.
How
Could
about you,
I-
Red? Good?
Yes, could I make an Excel sheet that just optimizes the ever-living hell out of this?
You could try.
Okay. I might after Wednesday.
By all means, you can do this however you find is easiest. But yeah, you can definitely try. I'm not opposed to it.
Emphasis on the word try.
It's formulaic, so for the most part, you probably could. Like, you have to type up the whole character table.
Yeah.
Yeah. That's a
That's the
lot of
worst.
characters. Oh, here, are we using this again in this course?
Nope.
Okay. Well,
I was
that
like,
gives
yeah, you want to like, there will be like IR charts that you make in the future, and it'll ask you questions about like, what do you expect to happen? And by all means, you could work through it if you really want to support your answer. Because usually those questions are looking for like some literature-based support or some theory-based support. So if you want
Alright.
to use this to support it, you can.
Okay.
But it does get
Alright.
difficult with hydrogen. So I always recommend just break off the hydrogens for metal complexes. So it'll get slightly different results, but
Excuse me. No, I like this process. There's just, I think, lots of locations where the dropping of a negative will colossally screw you up.
that's all good. You have checks, and usually if you drop a negative, it'll mess up one of the places to check. So the biggest place to make a mistake is in the irreducible representation, because you're really just changing out +1 with -1, at least with the examples we'll do in this class. So you get a wrong number, and then when you do your 3n check, it's not right.
I'm excited to try this out for real.
Alrighty, I think that's it. I'll go ahead and try to remind myself to post this. How do I? Ah. What just yelled at me? Oh, do I want to keep the ink annotations? I'm good.